Hey, Dr. Clark coming at you with another Check Your Understanding video. This time we're in section 7.5. 7.5 is focusing on Laplace Transforms method. In particular, we're looking at impulse forces. That's the key idea from section 5. Let's take a look at the problem. A spring mass damper setup has a mass of 1 kilogram, friction proportional to velocity with constant 4, and a spring that stretches 1 meter under a force of 13 newtons. An impulse force of 9 newtons is applied at t equals 4 seconds to a mass that is released from rest at a position 6 units to the right of equilibrium. Part A, write the initial value problem that models the scenario above. So the first thing we want to know for part A is the standard spring mass damper differential equation, which is mx double prime plus bx prime plus kx equals right-hand side forcing terms. They've told us that the mass is 1. They've told us that friction is proportional to velocity with constant force, so that's a 4x prime right there. And they've told us that a spring stretches 1 meter under a force of 13 newtons. So if the force is 13, then the x would be 1, and therefore the k, to make that equal, would have to be k equals 13. So the spring force constant is 13. Now, the right-hand side, the external forces, there's only a single impulse force of 9 newtons applied at t equals 4. So that's 9 dirac t minus 4. Remember, the dirac models impulse forcing. The time is at 4, and it's 9 newtons, so we have a 9 on the dirac. The initial conditions, x of 0 equals 6, x prime of 0 equals 0 because it is released from rest, indicating the velocity is 0, at a position 6 units to the right of equilibrium. So that is part A. We've modeled the scenario with this initial value problem right there. Now, they say, for part B, without solving, sketch a graph of the solution based on the physical description of the model. Well, this model is underdamped because the friction term is so much smaller than the spring term. If you want to be more specific, if you look at b squared minus 4ac, that's 16 minus 52 is negative, what is that, negative 36. So that's going to be a negative number, so that means we're underdamped. If we're underdamped, when we graph that, starting from position 6 at rest, we should expect the solution to decay down like so, some sort of decaying oscillation. But then at t equals 4, we have an impulse force of 9 newtons. That's going to shoot the graph back up, and then it will decay back down to 0 thereafter. And this is just a rough sketch. I don't know exactly what the period is, so you could probably do a slightly better sketch than this. I should be a little more consistent, but something like that. So that's a rough sketch in T, and maybe I should have used another color for the solution. There's the initial velocity coming in, impulse force, and then decaying back down to 0, essentially. So that is a rough sketch of the, quote, graph of the solution based on the physical description, knowing the fact that it's underdamped, and then adding in that impulse force at 4 seconds. Okay, and then for part C, we're going to need a new page. It just says use the method of Laplace to find the solution and compare it with your sketch in part B. So if I take Laplace of the differential equation using the linearity, I can write this as L of x double prime plus 4L of x prime plus 13L of x equals L of, well, I can use the linearity again, 9L of dirac t minus 4. And then I can start working this out using, first, there is this formula right here. I'm going to need that. I'm going to need the Laplace transform of the dirac. That's e to the minus s t naught. In this case, t naught is 4, but mainly we need that formula right there. So we will use that here. So this becomes s L of x prime minus x prime of 0 plus 4 parentheses s L of x minus x of 0 plus 13L of x. And that's 9 times e to the minus 4s. We ran out of room, so let's copy this equation here and start it on a new page. And continue the work. We already know that x prime of 0 is given as 0, and that x of 0 is given as 6. So this is 0 and this is 6. So this gives us now s, and then another parentheses, s L of x minus x of 0. This term here in blue contributing to this, plus 4s L of x minus 24. If we multiply the 6 and the 4, we get 24. And then 13L of x equals 9 e to the minus 4s. And then x of 0 again is 6. So this, all said and done, is s squared plus 4s plus 13L of x equals 6s plus 24 plus 9e to the minus 4s. We have a 6s right here, negative, that's added to the other side. We have a 24 that's added to the other side, and then the 9 already was there. And then I just collected the L of x terms. There's the characteristic equation as expected. I now can solve for L of x. And so I have 6s plus 24 over s squared plus 4s plus 13 plus e to the minus 4s times 9 over s squared plus 4s plus 13. Now, these look like irreducible quadratics in the denominator, so we complete the square. And because of the 4 here, we're going to have s plus 2. And s squared plus 4s plus 4 plus 9 would equal 13, right? So this is going to equal 9. So this can be factored into s plus 2 squared, which contributes a 4. 4 does not add up to 13, so that gives us the extra 9 right there. The numerator remains the same, 6s plus 24. And we do the same here, s plus 2 squared plus 9. Now, the first term here, we need to have s plus 2 squared. We need to have this s in the numerator match this s in the denominator, and it currently does not. But if I factor out a 6s plus 2, s plus 2 is equal to 6s plus 2 would equal 6x plus 12. And I have 6s plus 24, so there's actually an extra 12 left over. This here is equal to that because 6s plus 12 equals 6s plus 24. And actually that plus 12 is going to become its own term. So I'm going to actually write it as 12 over s plus 2 squared plus 9 and eliminate it from the first equation. Okay? And the second one, I have, I think I'm going to take out a 3 e to the minus 4s, and then leave that as 3 over s plus 2 squared plus 9, so that it matches the standard sine and cosine formulas that we're looking for. And what I mean by that is sine of kt is k over s squared plus k squared. So if k is equal to 3, I would get 3 over s squared plus 9. And that's what this is right there, 3 over s squared plus 9. And for cosine, I need s over s squared plus k squared. And so this one has 6s over s squared plus 9, right? So those terms are beginning to match the form I want. In fact, we probably could do slightly more work here. Let's just do one more step. S plus 2 squared plus 3 squared is 9, plus 4 times 3 over s plus 2 squared plus 3 squared. And then the last term, I'll just copy and paste it here. Okay, and now I'm going to use, so what we have here, we have an s into s plus 2 shift. That means that this, when I L inverse the right-hand side here to get my function x of t back, the first one is essentially going to be 6 times e to the negative 2t times L inverse of the standard s over s squared plus 3 squared, right? So this can be thought of as this s to s plus 2 shift, which generates an e to the negative 2t from the s plus 2 times L inverse of the standard, but the standard function is just cosine of 3t. So this will become 6 e to the negative 2t cosine of 3t. Okay? The second term also has the same s into s plus 2 shift. So this is going to become 4 times e to the minus 2t L inverse of the basic function, which is 3 over s squared plus 3 squared. And so that's going to be 4 e to the negative 2t times sine of 3t. And so now I've accounted for this, giving me 4e to the negative 2t sine of 3t, and this giving me 6e to the negative 2t cosine of 3t. What I haven't yet accounted for is this last term here. So there should be plus one more term. So let me grab these and slide them down ever so slightly to make a little bit of room. And let's think about this final term right here. And so what we need is we need L inverse of this. So the first thing we notice is we have this e to the minus 4s. E to the minus 4s means we're going to be shifted by 4 seconds. Whatever happens at the end, we're going to need a u t minus 4, and t's are going to be replaced with t minus 4. Okay? So if I keep that in mind and I look at, and I have the, I might as well take the 3 and just handle that right now. We've got this 3 right there, just write a 3 there. Now the question is, what is going to follow after that u? Well, the basic function here is 3 over s squared plus 9. That is, the basic function is sine of 3t. but it's been shifted s into s plus 2 in frequency space. So that means we're going to get an e to the negative 2t sine of 3t, but we're not done yet because those t's have to match t minus 4. So what we actually have to do here is have e to the minus 2 t minus 4 and sine of 3 t minus 4. And that is the final answer for L inverse of 3e to the minus 4s times 3 over s plus 2 squared plus 9. So if I paste that in down here, let's see, maybe I can get this plus sign out of the way and then move that up ever so slightly. That is the final answer right there. 6e to the minus 2t cosine of 3t plus 4e to the minus 2t sine of 3t plus 3u minus 4 times e to the minus 2t minus 4 times sine of 3t minus 4. And I went ahead and graphed that in Desmos. So this is just the exact same thing that I just wrote down a second ago. I created the unit step function here, and then I graphed it, and you'll notice the initial position is 6 with velocity 0. It decays down. At 4 seconds, we get an impulse force, which then decays down again, and that graph is a slightly better one compared to the version I drew at the beginning, but characteristically the same. So hopefully you were able to get that problem right. That's a challenging problem, so if you did get it, you should feel very good. There's a lot of moving parts in it. Yeah, I hope this video helped you out, and we'll see you next time.